So we're going to start section 5.5 with looking at some new notation for something and defining something called the indefinite integral. So if you remember, our definite integral that we've spent a lot of sections developing and working with was the idea of the limit of the sum. And so we were able to ultimately take the limit of those Riemann sums, and we were able to prove it with fundamental theorem of calculus that can actually be evaluated exactly with the antiderivative. So essentially, we're just going to kind of conveniently say, okay, well, if that definite integral is linked to the antiderivative, maybe we can just use that notation and not use those limits of integration, and let that be a new notation for finding the antiderivatives that we talked about in section 4.8. So this is our new notation. When you see this integral symbol without the limits of integration, that's going to tell you to just simply find the antiderivative plus c. So that whole family of antiderivatives when you add in that constant there. So what you see below, these are all of our antiderivatives that we had listed out in section 4.8, and now we can just write them with this more convenient integral notation instead of using, saying find the antiderivative or using the capital F for the antiderivative of lowercase f. We're going to now just rely a lot on this integral notation. So our first few examples here, we're just going to get warmed up and just use our new notation here, but we're just going to evaluate some antiderivatives that will really be like problems that we would have seen in section 4.8. So let's start with, example number 1, suppose I have the indefinite integral of x to the third minus 4 times the cube root of x plus 1. Now that we could take an antiderivative of or integrate term by term, but as soon as I do this, we're going to divide the whole thing by 2x. Now we have a quotient, and we can't take the integral or the antiderivative of a quotient by taking the quotient of the integral. So that's just kind of the first, big caution as we remember some of these things. Do not think that you can just say, oh, I'm just going to take, the antiderivative of each term in the numerator, and I'm just going to divide that by the antiderivative of the denominator. So this is something that we need to be careful not to do. So instead, we are really forced to think about simplifying this, or do the division, let's call it that. So we are going to do this division. Since we're just dividing by a monomial, we can divide each term in the numerator through by that monomial in the denominator. And then when we are dividing with the same base, we are going to subtract our exponents. So the first term, I'm going to think of that as 1/2, just a constant multiple is easier to look at. X to the second power minus, reducing 2, 4 divided by 2, and then x to the 1/3 minus 1. So 1/3 minus 3/3, that's an x to the negative 2/3. And then our last term here, again, a constant multiple of 1/2. This one I'm going to choose to leave as 1 over x. That's a little bit more, might remind us a little bit more about this being that one time when we don't do the power rule. So notice I've left my integral notation up until this point because I haven't yet integrated. Once you actually take the antiderivative, now you drop your, what I like to call the bookends on the problem. So it's the integral, and then the dx is telling us with respect to x. So let's go ahead and actually evaluate or take this antiderivative. So 1/2 gets carried along as our constant multiple, and then we're applying our power rules, so add 1 and divide by it, so x to the third over 3. And then again, the 2 gets carried along as a constant multiple, and x to the negative 2/3 plus 1, so negative 2/3 plus 3/3 would be x to the 1/3. And again, initially divided by that 1/3, but I definitely want you to clean up those complex fractions. Now, if you initially were thinking of this x as an x to the negative 1, that's fine, but the minute that you find yourself saying x to the 0 divided by 0, that will remind you, oh yeah, this is the one time when it's not a power rule situation. This antiderivative is our natural log of the absolute value of x, and we're not evaluating between limits of integration. So in this situation, we always need this plus c. So the only other thing I want us to do is clean this up a little bit. So the first term here is a 1/6 x to the third. Dividing by 1/3 is like multiplying by 3, so this is going to be minus 6, and our x to the 1/3, or cube root if you prefer. And then we'll just leave this as 1/2 natural log absolute value of x and plus c, but just at least cleaning up those complex fractions. Okay, so there's our first example, just kind of reviewing some of our power rules. Of course, that first required a little bit of dividing and simplifying there first. Okay, so let's look at another couple of examples here. So number 2, suppose we had the integral of 5 over the square root of 1 minus x squared dx. Now again, we don't have any sort of way to evaluate this, like in terms of taking the integral of the numerator divided by the integral of the denominator. Additionally, even if I could, we wouldn't know what the integral of the square root of 1 minus x squared is. We can't do integrals yet of anything with compositions or anything along those lines. All right, so instead, we just want to kind of think back, well, did I learn any derivatives throughout the semester any functions whose derivatives were the square root of 1 over 1 minus x squared? And we did. So in fact, if maybe I scroll down here, hopefully when you see like the 1 plus or minus x squared, maybe under a radical, maybe not, but hopefully those, even if you don't have those memorized at this point, hopefully it reminds you of those derivatives we learned of our inverse trig functions. So if you notice, we have that first one up here, that's on the top of the screen anyway. So we learned the derivative of arc sine was the 1 over square root of 1 minus x squared. So of course, the integral, or the antiderivative of that, is simply going to be 5 as a constant multiple, and then either sine inverse, or if you prefer, arc sine of x plus our arbitrary constant. All right, let's just take a look at one more. So again, all we're really doing here is just kind of reviewing some of our antiderivative rules, but essentially just using our integral, our indefinite integral notation here. So number 3, let's take a look at the integral of 2 cotangent squared of x dx. All right, so again, we have a composition in a way. It's cotangent quantity squared, and we also could think of as a product, cotangent times cotangent, none of which we can evaluate with our integrals. We don't have a product rule. We won't, in fact. So we need to just kind of think about, well, was this one of those, what I'd like to call special trig functions that we know antiderivatives of? Meaning, at the beginning of the semester, we learned several functions, or 6 in particular, trig functions, and we learned their derivatives. So what we want to think about is, well, were any of those ones whose derivatives were cotangent squared? And they're not, so I'm looking now back up here at the original 6 functions whose derivatives we learned, because of course now those are the ones whose antiderivatives we know. So it's again what I call this special group of 6, that for right now, that's all we know are those original 6 derivatives backwards. And none of those are cotan squared. But maybe you remember something about, there's some trig identities, in particular the Pythagorean identities, that will allow you to get the square of your trig functions in terms of a different square of a trig function, right? Like, you know, sine squared plus cosine squared equals 1. So if you had sine squared, you could replace it with 1 minus cosine squared. So when you see squares of trig functions, think Pythagorean identities. Now, in particular, the form of the Pythagorean identity, sine squared plus cosine squared equals 1, the form of that we want to use is that what we know is that 1 plus cotangent squared is equal to cosecant squared. I was never a fan of memorizing a lot, so for me, I would think about, you know, what the original one was, sine squared plus cosine squared equals 1, and I would think about just dividing that through by either sine squared. And so in this case, if you did that, if you divide everything through by sine squared, you get the 1 plus cotangent squared equals cosecant squared. Okay. Oh, my eraser was very big there. Let's rewrite this. All right. So that is going to allow us to then, just a second, let me clean this up here a little bit, sorry. So now, going back to what I was saying, so if we know that 1 plus cotangent squared is equal to cosecant squared, then we certainly know that cotangent squared is equal to cosecant squared of x minus 1. All right, well, that's good news. So now we can go back to where we're working here, and you can think of the 2 just as a multiple. In fact, you can bring constant multiples, as you see me starting to do, kind of just out in front of the whole indefinite integral. And then now we're going to replace our cotangent squared with the cosecant squared of x minus 1 dx. And we are allowed to take this integral or antiderivative term by term, and cosecant squared is one of the ones that we know. So the integral of cosecant squared is the opposite of cotangents. So this is going to be our negative cotan x, and then the antiderivative of 1 minus 1 is just minus 1x plus c. So notice now I've dropped my integral notation. Once I actually take that antiderivative, we keep it up until that point. Remember, with these, you can always check, like, oh, am I not maybe so sure about if I'm thinking and I'm not referencing the formulas, maybe I've forgotten 100% about if the negative's there or not. Well, check it out if you know your derivatives in a solid way. The derivative, if I check this, the derivative of cotan, if you remember, well, I know that's negative cosecant squared, and then times that negative, yep, that looks good, because now I get back to positive cosecant squared, and derivative of minus x is minus 1. So you can always be checking these. If you're a little more confident in your derivative knowledge, you can check those. All right, so that's basically it. If you want to just leave it like that, yeah, why not? If you wanted to distribute through the 2, you could. If you wanted to factor out a negative in front of that, you could. But that's it. So what we're going to talk about next time is where we're going to end the semester with a super, super important topic, really important as you get ready for Calc 2, which is integration by substitution. It will be our one and only technique that we work on this semester for situations that we can't reduce to term by term x's to powers, that we can't use trig identities and get it into a form that we know the antiderivative of. And so this is going to be the one and only technique that we're going to have to deal with these other situations. And so in this course, you'll learn lots of them in Calc 2, but in Calc 1, this will be it. So that's what we're going to come back and look at next time over the next few videos. It's a really, really important topic we're going to end the semester with. So that's it for this one.